Wade again with IDT, and in this installation of, or this installment of our PCI Express timing videos, we're going to talk about separate reference clocks and the impact on the clock selection there. As a separate reference clock implies, in this case I have my CPU box and my I/O storage block on the board. You know, we've got a clock generator that's feeding the CPU, and we have another clock generator that's feeding the I/O and the storage. And in this case, we're not going to be talking about spread spectrum, so there's no spread spectrum clocking here. So the impact on the timing is this. Before, with the common clock, it was assumed that the phase noise of the clock was common to both sides of your link, so you only had to do the difference function between the CPU, for instance, and the I/O storage SerDes, and to calculate. In this case, because there's a clock here and a clock here, I can't say that the phase noise due to the clock is the same. I have to allow for that separately. So I have to take a difference function between these two devices. So in this case, you know, this might be the phase noise of this guy, and this might be the phase noise of this guy. And this difference function of the clocks then also feeds into the difference function between, say, the CPU, the I/O, and the storage. So what this means is a couple of things. PCI Gen 3, the clock jitter spec for Gen 3 is 1 picosecond RMS. Okay, that's the common clock. I'm going to abbreviate common clock as CC. So that's when the clock's the same on both sides. Now we have two clocks involved, so you would think that really what we have to now have is each clock would have to be twice as good to maintain the same performance on the link. And as a rule of thumb, that is exactly the case. So for a clocking device to work in a separate clocking space architecture with no SSC, it would really need, instead of being 1 picosecond, it would have to be 0.7 picoseconds RMS. Because this is root mean squared, the 0.7 is actually twice as good because it's RMS, it's a square root, so it would be 1 over the square root of 2, which equals the 0.7 picoseconds RMS. So a clock that's really good for common clocking architectures is probably okay for separate clocking, but you need to check with IDT to make sure you're choosing the right part for your architecture, and you need to know what your architecture is. In this case, this was separate clocking with no SSC. There will be an installment coming up talking about separate clocking with SSC in the near future, so stay tuned to this channel. Thanks.